Imagine you have two separate chemical building blocks, a simple alcohol and a common alkyl halide. On their own, they're useful, but what if you wanted to fuse them together to create an ether, those versatile compounds found in everything from starting fluids to high-tech solvents? In the mid-19th century, Alexander Williamson figured out exactly how to do this. But the beauty of the Williamson ether synthesis isn't just that it works. It's how it reveals the fundamental dance of organic chemistry. Let's look at the overall map of this reaction. As you can see here, we start with an alcohol. Using a strong base, we transform that alcohol into an alkoxide ion. Then we introduce an alkyl halide. The result? An ether and a salt byproduct. It looks simple on paper, but if we zoom in on the molecular level, we can see a classic back attack mechanism in action. Let's visualize the first step. Picture our alcohol molecule. To make it reactive enough to build a new bond, we need to strip away that hydrogen atom on the oxygen. We do this by adding a strong base, like sodium hydride. Notice how the hydride ion, a hydrogen with an extra electron, snatches the proton away, leaving the oxygen with a negative charge. We now have an alkoxide ion. This oxygen is now electron-rich and very hungry for a positive nucleus to pair with. It has become a powerful nucleophile. Now, here is where the second player enters the stage, the alkyl halide. Let's look at this methyl bromide molecule. Because bromine is more electronegative than carbon, it's pulling electron density toward itself. This leaves the carbon with a partial positive charge, a perfect target. And here's the key insight. This reaction follows an SN2 mechanism. SN2 stands for substitution, nucleophilic, biomolecular. Watch what happens next. The negative oxygen doesn't wait for the bromine to leave. Instead, it attacks from the exact opposite side of the bromine atom. As the oxygen begins to form a new bond with the carbon, the bond between the carbon and the bromine begins to break simultaneously. There's a beautiful, fleeting moment called the transition state, where the carbon is momentarily bonded to both the oxygen and the bromine. Then, in one fluid motion, the bromine pops off as a leaving group, and our new ether bond is sealed. But wait, there's a catch. Does this work for every molecule? Let's try the same reaction, but this time, let's use a bulky, tertiary alkyl halide, like tert-butyl bromide. As the alkoxide tries to approach that central carbon, it hits a wall. These surrounding methyl groups act like a physical shield, creating what chemists call steric hindrance. The alkoxide simply can't get close enough to the carbon to attack. Instead of an ether, the alkoxide acts as a base and rips a hydrogen off the periphery, giving us an alkene instead. This is why, in a Williamson synthesis, we always want our target carbon to be as uncrowded as possible, ideally a primary halide. So, the next time you see an ether, remember the Williamson synthesis. It's a perfect demonstration of chemical strategy, knowing when to strip a proton away to create a hunter, and choosing a target that is open and vulnerable to attack. It's not just about mixing chemicals. It's about understanding the geometry of the microscopic world.